Number 10. The Martian atmosphere is 95% carbon dioxide, which sounds like a chemist's dream until you realize the air pressure sitting on your extraction. Equipment is roughly the same as what you'd feel 30 kilometers above Earth is surface. Carbon dioxide looks like the answer to almost every fuel and oxygen problem on Mars. Run it through the right reaction with hydrogen, and you get methane and water. Run electricity through it with the right catalyst, and you get oxygen. NASA's MOXY experiment on the Perseverance rover actually did this. It electrochemically split carbon dioxide into oxygen and carbon monoxide, producing about 6 grams of oxygen per hour during its test runs. That is a real confirmed result, not a simulation. The problem is scaling that to a human mission. You need roughly 1 metric ton of oxygen just for astronauts to breathe over a 500-day surface stay. MOXY at its tested scale would need years to produce that. A full-scale version would require enormous power, survive dust storms that cut solar generation by 90%, and operate flawlessly in temperature swings that crack metal. The atmosphere is there. Processing it is a different civilization of problems. Number 9. Water ice on Mars is real, confirmed, and distributed in massive quantities across the polar regions, and buried in mid-latitude deposits. And almost none of it is in a form that an early Mars base can actually use. The SHARAD radar instrument on the Mars Reconnaissance Orbiter has mapped glacial ice deposits, thick enough to flood the entire planet's surface to roughly 1 meter deep if melted. That measurement is not speculation. What the radar cannot tell you is how much dust, regolith, and perchlorate salt is mixed into that ice, and that mixture is the actual engineering problem. To extract water from subsurface ice, you need to melt it, or heat it with microwaves, or mine through frozen regolith with a drill that has never been tested at minus 70 degrees Celsius with no technician standing by to fix it. Every moving part becomes brittle. Every seal becomes a liability. Think of trying to run a commercial ice-making operation inside a walk-in freezer that nobody can enter, that nobody can fix, and that loses power for weeks during a dust storm. That is the situation. Number 8. Martian regolith, the loose soil and rock covering the surface, has been proposed as a construction material, an insulation layer, a radiation shield, and a source of iron, silicon, and aluminum. And it is also coated in some of the most biologically hostile chemistry found anywhere in the accessible solar system. Perchlorates were confirmed in Martian soil by the Phoenix lander in 2008, and have since been detected repeatedly across multiple landing sites. These are chlorine-based salts that dissolve in water, damage human thyroid function at small concentrations, and become reactive oxidizers when heated. Any process that involves heating regolith to extract metals or sinter it into bricks is going to activate those perchlorates, releasing chlorine gas and reactive compounds into your workspace. Proposals exist to wash the regolith or remove perchlorates chemically before processing, but washing requires water you do not have in abundance, and chemical treatment adds layers of complexity to a system that was already fragile. The regolith is simultaneously your best building material and a contamination problem wrapped around every piece of equipment you point at it. Number 7. Basalt is the dominant volcanic rock across huge regions of Mars. And on Earth, basalt fiber is used in construction, insulation, and composite manufacturing, which has led serious researchers to propose using Martian basalt to build habitats and structures without needing to ship material from home. The concept is not invented. The Mars Desert Research Station and various ESA-funded studies have explored basalt fiber production as a local construction strategy. Basalt melts at around 1400 degrees Celsius. On Earth, that heat comes from industrial furnaces powered by reliable electrical grids. On Mars, generating that kind of sustained thermal energy using solar power is a significant unsolved problem, especially with the solar irradiance at Mars running at roughly 43% of what Earth receives. You could use nuclear power, but no fission reactor has been surface deployed on Mars. You could concentrate sunlight with mirrors, but those mirrors must be manufactured, maintained, and protected from the same dust that coats everything within weeks of deployment. Basalt construction is not fantasy. It is just multiple engineering systems deep before the first brick exists. Number 6. Nitrogen makes up roughly 2.5% of the Martian atmosphere, which sounds thin until you understand that nitrogen is not optional. Every biological life support system, every breathable air mix, every plant growth chamber needs it, and there is almost none available. Earth's atmosphere is 78% nitrogen. Mars sits at 2.5% nitrogen by volume, but with total atmospheric pressure at roughly 600 pascals compared to Earth's 100,000 pascals, the actual amount of nitrogen available per cubic meter of Martian air is extraordinarily small. Separating it from the carbon dioxide using cryogenic distillation or membrane systems requires power, and hardware that must function continuously for months before you have enough stored nitrogen to pressurize a habitat. Studies on closed-loop plant growth for space applications consistently identify nitrogen as one of the hardest elements to cycle without losses. Every time you open an airlock, every biological process, every leak costs nitrogen you cannot easily replace. It is the invisible scarcity nobody puts in the mission renders. Number 5. Solar power on Mars works. Technically, the Opportunity rover ran for over 14 years using solar panels. The problem is that 14-year mission included multiple global dust storms where the rover survived by consuming almost no power and waiting, a strategy that does not translate to a crewed base with life support running continuously. The 2018 global dust storm that ended the InSight lander's seismic work ahead of schedule demonstrated how dramatically solar generation can collapse. During major storms, surface irradiance can drop to levels that barely maintain battery storage, let alone power electrolysis units, heating systems, habitat pressurization, and water extraction simultaneously. NASA's studies for human surface operations identify power as the central dependency that everything else chains to. If you enjoy thinking about how close these engineering margins actually run, the next few entries are where it gets even less forgiving, and it would mean a lot if you subscribed, so you do not miss what we cover next on this channel. Number 4. Wind on Mars looks like a free energy resource. The atmosphere moves. Dust devils hundreds of meters tall cross the surface regularly. Early mission proposals considered wind turbines as a supplementary power source. The reality is atmospheric density. Mars air is so thin that even a wind speed of 60 meters per second, which would be a dangerous hurricane on Earth, carries about the same kinetic energy as a gentle breeze of roughly 11 kilometers per hour in Earth conditions. A wind turbine blade that could capture meaningful power on Mars would need to be enormous, would need bearings and seals that resist dust intrusion over years, and would produce a fraction of what equivalent solar panels generate during clear conditions. Studies from groups including researchers at Georgia Tech have confirmed this limitation through atmospheric modeling. Wind is not useless, but it is not the backup power source the concept suggests. The physics of thin air defeats the intuition. Number 3. Martian dust is not just a nuisance coating solar panels. It is fine, electrostatically charged, perchlorate laced, and between 2 and 8 micrometers in particle size, small enough to penetrate any seal, not specifically engineered to exclude it, and large enough to abrade optical surfaces and mechanical interfaces over time. The InSight lander's seismic instruments documented dust accumulation rates that cut power generation measurably within months. Proposals for autonomous dust cleaning systems using electrostatic repulsion exist and have been tested in laboratory conditions, but sustained operation under Martian thermal cycling has not been validated at scale. Every pressurized vehicle, every spacesuit, every habitat airlock must solve the dust intrusion problem differently. It is the equivalent of building a hospital in a sandstorm, where the sand is mildly toxic and sticks to everything using static electricity. The dust is not the worst problem on Mars. It is the problem woven into every other problem. Number 2. Methane fuel production through the Sabatier reaction is probably the most seriously discussed ISRU application for Mars, and SpaceX's entire Starship return architecture depends on it. Carbon dioxide from the atmosphere plus hydrogen equals methane and water. Store the methane, electrolyze the water back into hydrogen and oxygen. Repeat. The chemistry is confirmed and has been used industrially on Earth for over a century. The catch is hydrogen. Mars has almost no accessible hydrogen in gaseous form. You have to source it from water ice, which requires drilling and extraction systems already discussed. Then electrolyze it, then react it with carbon dioxide, then liquefy and store the resulting methane at minus 161 degrees Celsius. Every step in that chain requires power, hardware, and operational continuity across a system that has never been run end-to-end in Martian conditions. A 2022 paper from researchers examining ISRU feasibility timelines estimated that a propellant production system capable of fueling a single Starship-class vehicle return would require, on the order of several hundred kilowatts of continuous power and years of pre-deployment operation before the first crewed mission lands. That is not a reason to abandon it. It is a reason to be honest about what the timeline actually requires. Number 1, liquid water on the Martian surface cannot exist under current conditions. The combination of low pressure and temperature means any liquid water exposed to the atmosphere immediately boils away or freezes. This is the triple point problem, and it governs every water-dependent process, from drinking to plant growth to chemical processing. The only way to work with liquid water on Mars is inside a pressurized, temperature-controlled environment. That environment must be built, sealed against dust, powered continuously, and maintained by systems that have no technician available for emergency repair. Every water-dependent ISRU process lives inside that pressurized bubble, which means water is not a raw Mars resource the way people picture it. It is a managed industrial product that requires infrastructure to exist before it can support any other infrastructure. Scientists at the Mars Institute and in ESA's human spaceflight. Planning groups have described this circular dependency as one of the foundational design challenges of any permanent Mars presence. You cannot build the infrastructure without water, and water requires infrastructure to be liquid. The resource is real. The access is the engineering civilization you have to build first. Every item on this list exists on Mars. None of them are myths. What sits between the resource and the use is the actual cost of becoming a multiplanetary species, and nobody has fully solved the tab yet.